Okay, question 9. What is the maximum load you can apply at E without toppling? So the green positions are my pivots, the red positions are my pivots, and the green positions where I'm applying loads. So when I'm applying the load here, I could either pivot at this point here. Well, I can't actually pivot at this point here because there's nothing to make me go around in that direction. Well, we've got this force here actually. Is that possible to pivot? So you've got 50 times 9. So that's trying to lift it off. And then you take away 100. So yeah, it could come off actually. So this force here could push it around and make it lift off. So there's a minimum and a maximum load that we could apply. Right. So usually it would be a case of where's your reaction going to be 0? Maximum, it would be pivoting around here. And so this reaction here would then become 0. So what you've got to do is work that out. So can you work out what the load is? Once you think you've done it, well, first of all, pause the video, and once you think you've done it, I'll show you the solution. Okay. So as I said, when you get a problem like this, maximum load or minimum load, it just becomes a seesaw problem. The question is which one is where your pivot is going to be. So what are we going to do for this case? We're going to apply a maximum load at the end. So we're going to therefore assume that this reaction at the other end there will be in effect 0, just at liftoff, as it were. So what I want to do is take moments about D, because I know what the reaction is at A by assumption, actually, or what kind of problem I'm dealing with. I've got an unknown at D, so if I take moments about that, then I'm going to get rid of that unknown, and I won't have to work it out, because I'm looking for the maximum load. So I don't need to know what the reaction is at RDY. So let's take moments about D. So the first one we can see is that we've got this load, LD we'll call it, LE we'll call it. It's 4 meters away, so it's going in a clockwise sense. Notice this 50 as we go around with our clock. So go around with our clock, that comes up, and this 50 force is also pointing upwards, so that's going to be a positive turning moment. So 50 times 5. Then I've got to measure, and I've done a typo here, haven't I? 212. 5. Oh no, what an idiot! I was looking for the distance up to here. So the distance I'm looking for is the other force is this distance here. So it's the 7 plus the 5, so that's 12, and the 100 is coming down, so it's going to be a negative turning moment. So there we go. That's my solution. Let's rearrange the maths. So the 50 times 5, take away the 100 times 12, and we end up with 950 divided by 4. So the answer you should have got, hopefully, was 237.5 kilonewtons. Okay.